I'm also currently a PhD candidate for computational chemistry, and my research is just based on graphical neural networks and graph theory to explain how molecules and drugs behave, whether it's a reaction or a drug. So today I'll be just giving a talk or a webinar on machine learning biased and explainable AI. I think explainable AI is currently a good topic or a hot topic, but we'll get into details. And also what is our bias within the machine learning model. So as I was saying, our current session will just be focusing on how to understand what could cause the bias within the ML machine learning system and how can we really see if the model is being biased towards a certain group and what impact can it have. So, and of course, we'll be performing some tests and also showing you the practical method on how to really go on with how do you solve the bias within your data set or your model if that's the situation. And we'll also apply the explainable AI to see how is the model making the predictions and what does it tell us, by the way. Explainable AI is not only just about really showing us how the prediction are made, but it can also help us to understand the data as well on how is everything going on within the data. Especially if the model is more accurate, then we can trust how it makes the prediction and what implication or what is it inferring or implying by those predictions. So the idea was also to go further into transfer learning and how to use scale up your model into a large data set, but we won't go through that due to time. So we'll only focus on explainable AI and the bias within the machine learning model. So to get into the details, what is a bias in machine learning model? A bias can be just a systematic error, but in most cases it's not. It's not a random one. It's either can be the data that is really telling you um, 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 is creating the unbiased, or it can be the model itself. But I won't be philosophical about it. But the truth of the matter is that it can have a huge impact into discriminating certain class of groups or people, and which most people they will say the machine learning model is discriminating you, while the model cannot really itself discriminate you. It's either the data or some systematic error that may lead to that. So um, where does the machine learning um, um, bias can be found? It can be either found in the data. So you can imagine if all of us, we would drink alcohol, but on my status, I post too many alcohols and they use that as my data. It will say I drink more than you. But the truth of the matter is that if the data is biased, and the model would be biased. But there are some cases where the data is not biased, the algorithm itself is biased. So those are the things that you need to look at when you're building your machine learning model, especially if you are looking into classification problems, which are very, very important to look into so that you can represent all classes equally, and so that if you use your model for recommendations or anything else, so it doesn't discriminate other people. So the real world impact include healthcare. The algorithm can, if the data is mainly based on based on white people, then black patients, they can be really into a risk because they may get less healthcare. And you can think about the hiring system, and if the model is basically have a lot of data based on men, it will probably favors men when it comes to hiring. So such things, they are very, very important to highlight and to make sure that the selective rate is equal. What is important is the selective rate to be equal. So the bias in AI does not create inequality. It just amplifies what has been there. So as I was saying, if the data is unequal, it reflects the inequality, then it just means that the model will favor the data, and then eventually it will discriminate other people. But I won't go into that more so. But what is the solution? The solution is just to find the trade-off where you can minimize your error and also minimize your bias. Try to make sure that you stay where the model within, so you don't move this way too much, because you might try to reduce the bias a lot and you end up having a huge error, which means your model is not accurate, but it's not biased, so which becomes useless. And as much as you don't want that, you can also try to make sure that your model is not too accurate and biased as well. So you just need to find a trade-off by finding the equilibrium of how do you minimize that. And again, so what I was just saying, or what I was talking about, is how do you quantify, how do you tell if a model is biased? You can tell it by quantifying the disparity. So you just check the model outcomes across all different groups. So you can see if the groups that having high percentage rate compared to the others, it can be either due to the data or the model itself. It just chooses to favorite other people over the other class, which could be very, very important to look at. And of course, I will show you in the details on how do we compute the disparity and so on and so on. When we look at the practical itself. And another thing, you can just check which is one of the most important one, is just to look at the spread impact ratio on how group A over group B, you're looking at the selection rate. So what is a selection rate? Selection rate is what is the model selecting, how much of a group is the model selecting. So you can imagine if within the group A is selecting 13%, at least we expect here to also select 13% in group B. So we wouldn't want it to select 15, here is 10. So it means already its selective rate is unequal. So what you're just gonna do, you're just gonna compute selection rate. Once you have those selection rate, you divide them. And if you have a lower score below 0.8, then it means it's biased, or maybe it's above 1.25. It means it fails to be fair. And of course, I'll get into the practicality of it. And again, you can look at the equality over equity. And what is also very important is that how can you try to put in the weight so that you make sure that all the groups are being favored, and so that because sometimes equality can mean a different thing. You can try to put the same weight within the model, then now it still favors the other ones over the other one, even worse. So you just need to find fairness. And fairness, it doesn't mean equal in most cases. It just means some already have the advantage. You just need to take the advantage off. That's what it means in a simple term. So you just need to take that advantage and put it on the one that are very advantaged, to try to minimize the bias. So those are the things that we were looking at. And as I was saying, you can visualize those, and they are you can compute those, so you see which outcomes have been favored by the model and which ones are not favored by the model, are not favored by the model. So which groups is privileged and which one is not privileged. And from there, of course, and you look at you're just gonna say 60. So for instance, if you have the parity difference, you're just looking at two groups. So you look at their favorites or selective rate, then you're just going to say 60% minus 50%. So it means there's that 10% difference. It tells you already that the selective rate is already, and you can just also see by your eyes that the selective rate it is not equal or fair. So how can you fix the bias within the model? Number one is just to look if your data is balanced or unbalanced. And before I just go into the practicality of it, there's some machine learning model that can work with or imbalanced data and that can work very well. So those are the things that you just need to be aware of. And another one, if you find that your data is unimbalanced, number two, what you can look at is to try to synthesize the data using resampling or synthetic data, such as you can use something called Smooth, which will try to find a way to add your data points within your data set that could make your data to be balanced. And what you need, of course, is a balanced data. And then in some cases, you can have, once you have a balanced data, then it's easy for you to make good prediction. But in some cases, you can use a weighting where you put weights within your model where now what you're looking at is the same as I was saying. You try to remove advantages from the ones that you know they already have advantage and try to elevate the ones that are disadvantaged. This is called giving weights towards your model, where now it can see, no, this group is already disadvantaged. Then you put ways to put it up, which I will show you in practicality. What does that mean and how do you go about it? And then from there, we'll look at the explainable AI. So there's a term that is used within neural networks. It's called black black box problem, which means that we don't know. We can see the model is accurate, but we don't know how it's making the prediction. Mainly because the data itself is complex. You can imagine if you are using voice recordings and how does the neural work can manage to make a prediction whether this person is speaking here is a male or female. So that already is a complex issue itself, and it's difficult sometimes to look inside the black box or the model itself and look at itself and see how is it making those predictions. And to be transparent, you can imagine if you go to a doctor and you have been sick for a whole week and it's bad, and you go to a doctor say, no, this is not a problem, I'll just give you a vaccine, without telling you anything at all. And of course, if you're oblivious or ignorant, you can take the vaccine, but if you're curious, you want to know, wow, what is the issue and why am I taking vaccine, not just a simple pill? And those are the things that matters a lot. What you are trying to do is to try to be able to see the predictions. How does it make the prediction? And those, if you are able to do that, that is called interpretable model. You can see how it's making the predictions and which features of the models are more important towards the prediction. And itself, it can also help you to analyze the data. I hope I'm not rushing. And what if I tell you that in most cases you can beat the black box, but it depends on the types of the model that you are using and the complexity of the data. So for you to beat those things, you just use explainable AI. And of course, there are why explainable AI. So what you can do, you can just see the prediction itself, as I was saying that, oh, these features are more important. Now you can visualize the model and see, okay. And to some extent, you can tell how each data point, not just only the prediction, but a specific data point that it can tell you how was the model able to make those predictions for the specific point, which is very, very interesting. And now you can tell whether you want to rely on that model or not based on what the information you are knowing about the model. So which is very important. However, some neural networks that are difficult to solve their black box. Even today, some people, they will still tell you that we don't know how LLM, of course, we know the theory behind LLMs, but some people, they will tell you we don't know the exact, how does it go about its predictions. So, which is very, very important, but there are people who are working on it and some have made some progress, but it's very, very difficult in some neural networks, especially when you are working with generative data. And explainable AI doesn't really tell you the theory of the model, but we are looking at how the data itself influence the prediction within the model. That's what matters. So that now we know what actually goes on within the model. And how does explainable AI? What you just do, you have a data, you put a model, you create a model, then you make a prediction. So from there, what you do, you apply your explainable AI method depending on what type of the method you are using or the model you are using. Then from there, you'll get the explanation. How did it get to this prediction? And why is it accurate so well, or why maybe it's not accurate, and you'll be able to see what's going on. And those are very important things within business because they really want to rely on the model, but they want to know how does it make the predictions. And that's what really matters. So one of the way to to tell within to explain your model can be feature importance. So feature importance, what you are looking at the contribution of each feature within the model. So you can see credit history contributes about 88% within the prediction. So compared to income, and you look at the employment length within your model doesn't contribute a lot. It's like 4% so far. So what does that tell you is that the model relies mainly on the credit history to predict whatever the outcome that it want to predict. So which in this case, the idea was just to check the influence within the overall or credit risk model. So you can see the credit history for you in order to get uh, um, the credit history have so much percentage. So the other method that we use is Sharp. And how does Sharp work? Sharp, it just look at it- for instance, you have two class of people, and it looks at the two classes and try to relate in terms of the features, which ones are more important. And what that can even end up telling you is that you can end up knowing that this class, which is the blue, I don't know if you can see my cursor, the blue one, it also, it can also tell you about the impact within the model that, for instance, let's say this is a body mass, the one with people with lower body mass, they also contribute a lot. And you also have the body mass in between the blue and the green, and you also have the red ones, which there are not a lot of them, but overall, the body mass feature, it does contribute to the model's predictions. It doesn't only tell you about the feature itself, it tells you about the feature in terms of whether the feature is low and whether the feature is high. So when you have high feature, does it impact the model negatively? Which means yes, this side, does it affect it? How? And those are the things that you can be able to know, which will go further when we look into the practical. Then you also have Lime. Lime is mostly used within neural networks. So Lime, you can imagine it as you have three people and you tell them to move tables from this venue to this venue. There are three of them. And when you come back, you find that they have done the work and only 90 of them, and you had 100 table, only 95 of the table, they have been moved. So now you are trying to anticipate how did these people manage to move the 95 within this time frame? What you can do, you can just remove person A by permutation. So what you do, you leave only two people and you see how far they will manage to do the same task within the same time frame. And when you come back, you look at it today. Now it's no longer 95 of the tables being moved is 64. So already now tomorrow you're also gonna remove the person B. You remove person A and person B. You only leave person C to do the work alone and see how far he can contribute to the task within that certain time frame. And eventually when you start to look, and tomorrow you still continue, but now you start removing from person C, you leave person A and B now. So eventually to see their importance by permutation. That's what it does. And we use it mostly within neural network because it's quite, and when we are looking at the feature to explain each and every feature, how important when you tick out the data. So you're just removing a feature by feature and see how much of the features that left contribute to the point that you remove all the features, you are left with one. So that's what it does in simple terms. So, and as I was saying, we'll look at and at how do you really go on about the bias and how do you mitigate it, and we'll also look at the how do you build an explainable AI model in simple terms. One of the difficult thing it was to find the data that you can really try to show this thing in real life, but there are many data where you can really see the how the model can be biased. So today's task, last time what we talked about, it was how you can use machine learning model for regression and classification. Today's task is classification. And some people, they call it binary classification predictions. So what are we doing? We're going to try to tell if something is not A or B. So we just check, is it A or B? We are not really interested in looking for the exact values such. So the data that I found out there, it was um, uh, okay. So the data that I found, it was the data from let me try to show you our data set. This is our data set that we are using. So this data set, just to go a little bit about what is the data set about, it was given to us, it was census. What does census do in most cases? Go to houses and check how many people live in this house and who gets the income within the house and how much does he get. So in this case, they didn't give us the real figure, so they will just say this person earns above 50K, this person and less than 50K. So we either have the people who are earning above 50K, which we'll call them, I don't know whether to call them good earners, and we also have low class, which are earning less than 50K. This is an annual rate. So that's what it was looking at. And of course, they collect the age, and they collect how many years you went to school, and what else do they collect? The types of work that you are working and the hours, whether you're female or male, your race, and so on and so on. So the moment you start to include race and um, and and uh, and your gender, it start to, or your sex, it start to really start to tell you the detail within the social studies. So now you can tell whether the females are earning less or more, so on and so on. So now what we're just gonna do, this is the link towards the data. So I'm just gonna be collecting them. These are their columns names. And I don't know, maybe I should restart and clear output. So I was just checking if everything is working. So, but just to be on the same track, so I explain each part by part. So these are the names of which I was talking about, the working class, and you have education, number of educations, marital status, occupation, relationship, race, sex, capital gain, capital loss, hours per week, native country. Then you also have, which is your important thing, and income, how much are you earning? So from there, what we're just gonna do, we collect the data frame, and then from there, we're just gonna, in the data, then we'll just convert it to the data frame using data frame. I believe last time I did tell you we use pandas for that. So we're just gonna read our URL. This is the names of the columns, number of non-values. If we have empty columns, you should put them as nones. And then we're just gonna skip initial space because the data set itself, there's an empty space. So we're just gonna to skip it off. So from there, what we're just gonna do, we just want to clean the income because we have is measured with 50K, is either 50K or not 50K. So what we're gonna do, we're just gonna compute it to Let me try this. Um, okay, my bad. So now what we're gonna do, we're just gonna, so the ones that ends 50K, it's gonna give them a value of 1 because the model itself cannot read strings or words. We need values. And the one that is less than 50K, it will be 0. So that's what I'm doing there. And I'll try to show you the data frame here. How does it look like? So this is how the data frame look like, where you can see we have 16 columns. And then now you can see this is the income in terms of binary, but before the income is either less than 50, equal or less than 50K or above. So unfortunately, we don't see the above one because most of them they are less than 50. Oh, here's the above one. So you can see the greater than 50K. So now let's look at the shape so we can tell how big is our data set. And our data set is about the 32,000. So, and how many? So what I'm gonna do, I just want to check the list of the features that I'm having, which is the ones that I explained previously, the relationship and so on and so on. So whether you are married or not. So I don't think whether you are married or not, it influences your income. I don't know when people are hiring, maybe it's something that they take into account. Then already that tells you that they're discriminating, but it's fine. So it's not going to be the model that will be discriminating. So if people who married, they get to earn more, then that's already tells you about the bias of the community itself more than the model. So the data will be biased. So what I'm choosing, I'm just choosing to run over 30,000. I'm not really discarding. I was just looking at the time that we don't want it to train for too long while we are waiting. So what I'm just gonna do here, I'm just going to look for the categorical data, which is sex, race, and encode them as well, so that they are encoded, as you can see here, uh, white, male. So we don't want these things to be like this, and marital status. So we don't want them to be as strings. We want to encode them. So we're just going to try to find a way to encode them. So we're still going to look. This is because I used only 30,000 there. So let's check how many males do we have. So we have 66% of male within our data set and 33% is our females. So that's with the whole data set. So now let's try to check how many people that are earning above 50K in terms of sex. You can see female out of is only 11% from the whole data set and male is 30% from the whole data set of the male. So what we're just doing, you're just dividing from the percentage that we had, those actual value from the whole data set. So from there, we can also look at the race again as well and see how does the race being favored above 50K. You can see 25% of white within the data set. They are earning about 50. They're earning about 50K, and also the Asians, they're earning above 50K. So that's the data. That's what we have so far. So what we're also gonna look at is the age. So with the age, we're not seeing much because we're just looking at whether less than 50K or above 50K. So it's not does not really tell us anything much about that. And we're also gonna look at the education itself. How does it impact your your earning? So based on number of education or years of education, so if you studied for 16 years, you are likely, people who studied 16 years, they have 73% of them, they're earning about 50K, which is nice. And you also have people who went to school for for 2 years, only 4% of them, they are earning about 50K. So that's mainly data analysis. I was just trying to get my head um, on, on, on that. So now we're just gonna move from this data analysis because I'm just running out of time. So this is the features that I'm gonna use for our models to train. So I'm choosing age, and I'm choosing education, number of years, how many hours do you work, sex, race, and occupation, which job are you working? So I'm not gonna look at the relationship. That's my own opinion, of course, but you can also see how does it really helps to look at the relationship. For me, I just think it's noise, hence I'm not including the other ones, whether your relationship and so on and so on. But the reason why I'm including sex is just to see, and race is just to see how selective the data it is. So how can we navigate around it to reduce the bias? So I'm just gonna move pretty quick. And so this is the data that we will be working with. So you just have age, number of years, hours per week, sex and race, as I said. And I just want us to move. Then this is our encoded above 50K or below 50K. So now I just also need to re-encode because I'm seeing we still have this and this. I just need to encode my categorical data. So these are the features that need to be encoded. Then I'm just going to encode them here. And then here it explained to us for sex. If you're a female, it gives you 0. Then that's how it encodes. Male is 1. So now we go to race because we have many races. We have 0, 1, 2, 3. So this is how they are being represented within the data set. And then we're going to scale numerical data. So what we mean by standard scaling. So we don't want to have values like these. They sometimes make the model to suffer 27, 48. We're just going to standards or scale them between 0 and 1. So there will be these values. For instance, 27 will be 0.27. This will be 0.25. I'm just giving an example. So that's what we mean by scaling or standard scaling. So you're just scaling the values so that the model can learn better. It helps the model. So you can see, of course, it gave them the values. So now the age, which was 24, now is 0.84. So it's just scaling the data. Instead of using the real or the raw data, we're just scaling them. That's what we mean by scaling them. So that's the data we have. So we're going to separate the one from test to train set. I just want to move a little bit faster. And of course, our data is quite big. So if I'm not using my laptop, so I'm using a server, so it will be relatively quick, I would like to assume. So what we're going to start with is the SMV, support vector machine, or the C is for classifier. So because we're using a classification, we are using the classification model for it. So last time I did explain about classification or how SMV works. It just works like linear regression, but its work is just to separate the two classes using a linear by minimizing the margin or maximizing the margin, sorry. So now we're going to get the training accuracy, and this is 72%, I mean, which is good, which is relatively good, not very good, but relatively good. And we're also going to use the XGM boost classifier. And last time I did tell you that when you use things like XGM boost, they're quite, you use them for good or better accuracy. So we're just going to run it and see the accuracy itself. And you can see the accuracy when you are training them is 0.81, which is very, very good from my point of view, because we haven't fine-tuned the model yet. And now what we're going to do, we're just going to try to find how many of the values did it get them right and how many did it get them wrong. So because so we can't really see the whole data set. Let's try to find a better way to visualize what we are seeing there on the data frame. So this is what I'm looking for. So you have a selection you have here what you are having, you have a selection rate. As I was saying, selection rate, you can just identify it as a how many, it's like how many out of the people that we are having. For instance, for male, out of 100 males, it will get the 24 of them correct. So instead of getting them wrong, so now you're looking at the true value. How many did it get correct? Is you just have 53 percent, and then this is the count. But be careful here because what you're looking at is the test set. We are testing it. So hence, what you're looking at, the values, they are quite a little bit small. So just now what we're gonna compute, as I was saying, you use the selection rate to look if something is fair or not. So this is your selection rate. And what you're gonna do, just gonna divide this by this to check the disparity. So the disparity is way too low. It's way too low. It's not even 0.5, it's 0.0 something. What does it tell you? It tells you that the males are being favored, or your model is likely to favor males or get the predictions about male correct. So that's what it tells you. But we'll just go a little bit further, and of course here it's just using the difference, which I was telling you about, the equal disparity. You can tell it's not zero. If the value was zero, then we'll know this group are being treated equal within the model, but they are not. That's the part of it. So for now, we're just going to create a little bit of, again, we're just looking at the Y predicted XTM boost. We're doing the same here. We're just looking at the selection rate. Again, as you can tell, it's not that good. So now we're just going to compute the summary of the bias. I think this will make more sense. We look at the accuracy. This is the accuracy, by the way. The accuracy and selective rate are two different things. The model can be accurate, but how much is it selecting the group equally? No, it's not. But the model, it is accurate. And you look at the accuracy of it, and you look at the XGM boost. For the female, the accuracy is 84. So it's getting 84% accurate. But here on the male is 0.66. Already is less accurate on the male people or on the male data. So, and as I was saying that this is your, here what you're looking at is your selective rate. Let's just move to race. And then here you can look at race. Let's look at the selective rate. So the selective rate here, you can look at the Indians. They have very, very low selective rate. So which means the model select them way too less. We're not looking at the accuracy when we are looking at the bias. It's not appropriate for us to use the accuracy. We look at the selective rate, not the accuracy. The accuracy, we're not going to be looking at it for now, but we're just looking at the selective rate. How does it select and make the predict in terms of the group itself? So now you look at the selective rate here is 0.1, but you look at here, the selective rate is way too high. So it means it is still preferring to use white, and it select the more outcomes they will favor white. So especially when you are looking at the people who are earning above 50K. So we're only looking at the people, the selective rate is about people who are earning above 50K. So which means that white people, they are more likely to be selected. If you were gonna to input a data here and say, I have a white, a male white, blah, 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 it will likely, the selective rate based on the model, it will likely to put him based on within the 50K, but we can't make such assumptions. We need to look at the explainable AI of which other features they do contribute, of course. But for now, we're just looking at the biases. And of course, the selective rate Hence, the selective rates are very low because there are other features that are contributing as well towards the predictions. So now what we are looking at again is for sex, the original, but we are looking at the XGM boost. I'm just gonna run away, I think, to avoid running out of time. To try to visualize so that it makes sense when I'm talking about the selective rate. So here we are looking at the boost method. So you are looking at the selective rate. Here you are seeing that the white, they are being favored, and also the Indian. So compared to black, I don't know what is others. I don't know the other ones. And then also the Indians as well. So now we're going to look at the sharp to explain to us why is this case. So we're going to run sharp. But one thing I need to get into, when you are using sharp, sharp has many different explanations because XGM Boost, it uses trees, like I was saying last time. So we're going to use tree. We're going to say sharp.tree explainer so that we put the XGM Boost model. Then we ask it to explain for us. Then here what you have, you're going to have the sharp values. This is your test. Of course, we're using the test values. Then you have the features names, which are the features names that we had above, the ones that we were training them with. So now let's look at them here. Now, what you are looking at here, I want to look at the first plot here. So it's telling us people with who are young, that's explainable AI. It's telling us people who are young, they are not earning above 50K. Hence, the blue, it means young or low in terms of the value of your feature, and the red means high. So in terms of data feature, and the ones that are a bit older, maybe 50 or something, they tend to earn more. But what does it tell us overall in terms of the feature? It tells us the age is very important, and which will make sense now because we assume that if you go to a company tomorrow while you're 24, you're going to start at a level where you're just a trainee, then eventually they promote you. The next thing you are a CEO when you are about 40 or 60. And most of the jobs, they work like that. And the number of the education or number of years you went to school, it also determines that. And if you went to school for way less years, then you are not likely to be above 50K or earn more than 50K. That's what the model is saying, and that's how it's making the prediction. Then it look at the sex. So it's saying, you remember our female, we put them 0, and our male is 1, so which means 1 is high. And what you're looking at now is saying females, they are earning less. Females, they are earning less than 50K. They are likely to, and most of females, they are likely to earn less than 50K, and you have male earning about 50K. And then in terms of occupation, it's a little bit mixed. So you cannot really tell what's going on. It's a little bit mixed, but then you go to a race where now you have a race that's on the middle, which is very weird. And while the other races, I forgot the encoding of the other races, and then you have the other races being both sides, but you have the race that is standing right on the middle. So which means, in other words, the race you can either earn based on the model saying it can be either you're earning about 50K or less. So that's what it's based on. So we can look at the features in terms of how much of the impact they have towards the model. So you say, as we were talking about, is the age, education, sex. Sex is also contributing. So which means, as I was saying, you can see that there were males that are there likely and which introduced the bias within our model. So now you have occupation, you have hours per week, which it should also contribute towards whether you're going to earn more or less than 50K. So you have race. So race doesn't really, it doesn't, the model in itself, it doesn't really put much heavy of the prediction on race. So, so now you can also just check how does it really sharp look at the age itself, which this is shows your age, and you're also evaluating according to education number of years. So as you can see, this will tell you whether it influences positively or negatively and how. When they are low, as you can see, when they are low and your number of years or education, it influences both. So there's not much of a correlation, just a mix, but you can have a correlation, but it's not an exact correlation where we see the blue ones here and the red ones here, where we can say, ah, this is what we are seeing there. So that is that. And oh boy, I believe that's a warning. Uh, so this is for SMV. I usually don't trust SMV because it's a, so now we're looking at the SMV one. It's the same ideology that I was talking about. But here, what he's saying is say we'll rather rely mainly on the education. That's SMV now. It's telling a different story from the XGM boost. So the SMV is saying that I rely mainly on the on the education, how many years you went to school compared to your age. So, but also age and education, they're relatively they have similar impact, but we don't know because here doesn't really show you the impact itself, but it shows you if they are rates, which means if you are old, you are earning about 50K, you are within the right side. So it means you are earning 50K, and if you are within the left side, which is the blue one, which means you are still young and you are earning how much. But we can look at that data or the value when we are looking at the bar where it tells us the impact within the model. So the impact is there's a huge difference in terms of the impact of the age and number of education we went to school within the SMV. This is the difference that you are seeing, that the model is heavily relying on education and number of ages. So if you are a person and you are building a tool and you know that your model is not is a little bit biased, what you can do now, you already have something to chew on. You can tell that, oh, race is not included that much, but sex also have impact, which means that now when you make prediction based on as you say this person is a female, then he might be put within the people who are earning 50Ks or male, depending on the data set that you are having. So you can also do something where you're looking at the individual feature, but it's just going to give me a warning because I don't think I have the right tools to visualize that. So, so now what I'm trying to do, I'm trying to fix that model that we had there, the XGM boost, because we saw on race and sex, it was not doing very well. So what I'm just going to try to do here, this is just splitting the train and the X, just like what we did before. But what I'm just going to try to do is try to compute weights and see if when I include the weights, when I get the selective rate equal, because I want the selective rate to be equal so that when it makes the prediction, because we can see that sex does have a does have an impact within the model itself when it's making prediction. We need to make sure that the selective rate is equal. So that's what we want. We just want the selective rate to be equal. So we're just gonna sample in the weight. So we're just gonna compute the weight. So what we are doing when we are putting in the weights, we're just saying, have a look on your weights and tell us what you're gonna get. I'll just try to rush in because I'm seeing that I'm out of time already. And this is how the weights looks like, by the way. These are the weights. And I'm just trying to run a little bit fast. Uh, this is the encoded data, so we don't need to worry about that. Now let's try to train and make prediction and see if we can get it to be a little bit fair. Okay. when we put the weights, it get worse. It get worse because now we have, but it's not that worse compared to previous one. We are looking at the XGM boost here. So we only have this one, that is where you can see these are relatively equal. So which means if we were to use this model now, it will discriminate the Indians. So that's what's going to be happening depending on the reference that we are using. So if we're going to use white as reference, we're just going to say 0.17. I mean, we're going to say 0.08 divided by 0.17. So what we're going to, it's going to tell us, it's going to say, it's going to favor everyone else except the Indian. So what can we try to do? Another best approach, which I didn't talk about when I was just presenting theories, that there's something called post-processing, where now you are saying, okay, now I'm getting this. I'm not going to retrain it at all, but I'm just going to try to adjust the weights now and see if the model can be a little bit better. And after adjusting the weights, uh, at each weight, so what I'm just timesing, I'm timesing it by 2.5. Of course, you can reduce the values until you get the right value. So we're just gonna try and see after the pre-processing if we are winning or not. So let's see the table, if the model is being fair. So it takes a minute or so. So let's just be patient and I hope it will give us good news. Of course, myself, I can't see because there's how do I remove this thing here? How do I reduce it? Uh, I'm trying to reduce okay, it's been reduced. Now I can see. Oh, okay. Now it's overestimating it. Whew. This is bad news. But what we can play around here now, what we're just going to be playing around here is the how much, because it was very low, we times it by that. And let's try to say one. Let's put 1.5 here. And let's see what will happen. So we're just going to configure. We're just not going to move by too much until we get the selective rate to be equal. That's what we're interested in. We want to be fair on the race, but you can do this on the other classes like your sex and so on if they are unequal, where you just do, oh, it's 2.1, but 2.1 is not, it's not different from 1.9, I mean 0.9. So actually, it's now being fair. If you look at the value, they are not far apart from each other. So if you were to divide this, if you were to say, I'm lazy, so I'm just gonna, will it allow me to copy? Okay. I'm just gonna use y as my relative value. Just wanna see. I hope it's not double. Okay, so it's 1 point, it's not about above 1.125, so it's fair. So which means now we managed to mitigate our model to be fair. So because we saw that the race is also have an influence, but not much of an influence, but also the sex it does. So you can do the same for sex and not really the occupation, but the sex and the others that you may be having as a classes of people or so on. I think I'm done there, and